Today we're going to learn how to perform double and triple integrals in MATLAB using the trapezoid rule, and then we'll learn how to do it using some built-in functions in MATLAB. Okay. And so in order to use the trapezoid rule to do this, we're going to need to think about the integral that we're looking at here a little bit differently. We're going to think about it as the integral from -2 to 2 of the integral from -2 to 2 of e to the minus x squared minus y squared dx and then dy. So what we'll be doing is integrating with respect to x first, and then we'll integrate with respect to y after that. And so is what I want you to kind of think about is if we were to pick some specific y values to find the integral. Okay, so let me show you what I mean. If I were to say if I wanted to find the integral when y is 0, so I want to integrate with respect to x, but I'm fixing y to be 0, then we'd be finding the area underneath this curve that I'm sketching here. Okay. And if I wanted to do that at, say, 1 or -1, looks something like this. And of course, and we could do lots of these, okay? But these are all, what I've sketched here are some integrals with respect to x, okay? So what we'll do is we'll actually use the trapezoid rule to find these areas, because these are just areas if we fix y, areas underneath these curves we've just sketched, okay? All right, I've zoomed this out a little bit, and I've given us a set of axes here. But imagine if you were to do a bunch of these little integrals. Okay. Right? Because these are just 2D now. Okay, these individual integrals that I'm talking about. Okay. Well, they're going to give you a bunch of outputs if you were to take those integrals. Like you'd get, it looks like if we were close to -2, be something pretty small, and as we and I'm actually going to extend my x-axis here so that my picture makes a little bit more sense. Okay, there's our y-axis. Now if I were to take some of those integrals, again at -2 it's looking pretty low, and it looks like these things gradually get bigger and bigger. Okay. And then they hit a point, it looks like, where they kind of level off. And then they lower back down again. Okay. So my axes here, though, let's think about what the axes are in this picture I just sketched. Okay. Well, these integrals were based on fixed values of y. And on the x-axis is what we're measuring here are these integrals with respect to x. I'm going to say I sub x. Okay. So these dots here are just a bunch of these calculations in here, a bunch of these integrals with respect to x for fixed values of y. Okay. And then after we do that, we could perform the trapezoid rule on this collection of points. Okay, and that'll give us our final answer. Okay, so trapezoid rule to evaluate the inner integral, okay, for fixed values of y, and then the trapezoid rule to deal with its outputs. Okay, so we can integrate with respect to y. Okay, let's go into MATLAB and see what this looks like. So I already have our function in here, and we've used mesh grid here to set up our x and our y. And then z here are outputs, and then surf. Okay. But we've actually already seen the output. It was this thing. Okay. This is just for visualization purposes. But let's go ahead and start setting up a function that does something specific for us, and we'll come back to the script. Okay. I want us to set up an integral or a function that will calculate those integrals for fixed y's like we were talking. So I'm going to say function, the output I'm going to put in here is int wrt x. And so is what I'm trying to say we're doing here is we're integrating with respect to x. And this thing is going to be equal to capital X integral. Okay. Again, trying to say we're integrating with respect to x, but we're going to do it for a specific y value. Okay. And let's go ahead and put f in here, our function. Okay. Well, we have already seen the function that we are trying to integrate. It looks like this: e to the minus x squared minus y squared. Okay. And note, only one variable here because we are going to fix y. We're going to fix y with whatever this input is here. Okay. We can go ahead and suppress the function. And then let's write in what our output, int wrt x is equal to trap. So we're just going to use the trap function that we built. So trap, the function f, and one thing you might not remember from the picture, but I do have it in here in our script, we're going to try and integrate the function over the region -2 to 2 in the x and then -2 to 2 in the y. So that's a rectangular region that we're integrating over. And so consequently, I'm going to put -2 to 2 here. And the only question is, what do we want to make for our number of subintervals? Let's go with 10 subintervals. Okay. 10 subintervals. And I'm going to put an extra comment in here. Okay. And this was our choice. Okay, we chose to use 10 subintervals. If you want it to be more accurate, you can choose more using the same technique that we're about to use here. Okay. But this is good. This is our function that will do exactly what we want it to. Okay, and we could test it out here in the command window, I suppose, make sure it gives us an output. So if we were to say do x integral, okay, and we saw that the biggest one it looked like would probably be when y is 0, so let's try that one out. And I spelt it wrong. I meant x integral. There we go. There's our answer. And I imagine as we get further out, like say at -2, it's probably pretty small. Okay. So it seems to be behaving the way that we might expect. Okay. Let's switch over. All right, and let's move down here a little bit. Okay. And so now we're going to be trying to perform the trapezoid rule. Okay, so I want us to first point out that we were using 10 subintervals. Okay, we chose this. Okay, after that, the question might be, well, in this picture on this page, these blue dots, remember each one of these blue dots represented one of these red integrals here. And so the question is, how far are those spaced out? Okay. Well, we're breaking the interval -2 to 2 into 10 pieces. Okay. So this thing has a length. The length of this is 4, and we're going to break it into 10 subintervals. So this right here is going to be the width of our subintervals. Okay. Should be the length of the interval divided by the number of subintervals. Okay. So delta y, the spacing of our y values, is equal to 4 divided by n. Okay? And again, we will comment in here that this is the width of the subintervals. That might be helpful at some point to us. And then next, we're going to set up a linspace vector that contains our equally spaced points. So y equals linspace. We want to go -2 to 2. Okay. And now, if you have n subintervals, that means that you have n points, or sorry, n plus 1 points. Okay. So if we have 10 subintervals, we're going to have 11 points that we're working with. So I'm just going to write in here n plus 1, but typing in 11 would have been sufficient as well. Okay. And now, this next part here, okay, we are going to start or write in our first term from the trapezoid rule in some sense. I say first term, I just mean, hey, we're going to start off with saying the volume is 0, and then we'll add stuff to it, okay, once we get our for loop going here. So trap rule volume, okay, and then for I equals 1 to n. So we're finally into the for loop here. Okay. And I want to remind you all where we're headed. Okay. So if I were to select this, remember, we are going to evaluate this. This is that int with respect to x. Okay. That's what this is in here. Okay. And we want to take these results, okay, these results here, and perform the trapezoid rule on them. Okay. But here we have integrated with respect to x, and now we are going to integrate with respect to y. Okay. So let's go ahead and take care of that. Okay. But the key is, though, is that the function that we're integrating is we're really going to integrate this integral here. Okay. Let's go ahead and write this. So we have and I'm going to just copy trap volume so I don't have to type it in so many times. So we have trap volume is equal to trap roll volume plus, okay, and this is where the formula for our trapezoid rule comes into play, right? We want to do 1/2 times, okay, and we want to then add up the two integrals, or two consecutive integrals that we're working with. So x integral, right, this is from our function up here, x integral, and we'd like to do this with the first element, so y sub I, plus, let me add in one more thing here. Okay. So far, I have, looks like the right amount of parentheses. So I have x integral of y of I plus x integral of y of I plus 1. Okay. So when I equals 1, it's going to do y of 1 plus y of 2 times 1/2. When I equals 2, we'll have y of 2 plus y of 3 being plugged into this integral function. Okay. So here's the 1/2, right? That's part of the trapezoid rule. Okay. Here's the sum of the two outputs that we're working with in our trapezoid rule. And then we don't want to forget the thickness of the interval here. So I'm going to say delta y, okay, which we've already defined up above. And then we'll go ahead and we'll end this. All we have left here for our trapezoid rule is to just take a look at our output, which I want to be below end here. Let's give that a run. Okay. And so we can see our volume, It's 3.1056. Let's compare this with MATLAB's built-in integral function for double integrals. It's integral 2, and you type in your function, which we'll need to define that here in a minute, and then we want to go -2 to 2 in the x and -2 to 2 in the y, and all I need to do is say what the function is. So f of xy is equal to the exponential of minus x squared minus y squared. Let's say int or built-in, maybe built-in function. Volume. There we go. Built-in function volume compared to our trapezoid rule volume. Okay, and they're pretty close. Even though we only used 10 subintervals for our trapezoid rule, and we could have used a lot more, we're pretty accurate. The next thing I want to show you is that we can actually also use integral 2 to integrate over regions that are not rectangular. So I'm going to assign this to have the variable name not rectangular. Not a rectangular region is what I mean. Integral 2. And I'll plug in my function f. I want x to go from 0 to 2. You can see I've changed up the region here. So 0 to 2. Okay. And then we want to go 0 to x squared. Okay. But keep in mind that this x here is a variable here, so I want to say at x here. There we go. And that will get it done. That'll give us our integral over this non-rectangular region. Let's see what we get. Okay. It should be something different. This is a different region. Okay. So we got our answer there. And I also want to point out that there is a built-in function for triple integrals. And you might imagine it is integral 3. Okay. And so I have another function here for us just to test out. So we have x, y, z, and then we're going to have x squared plus y squared plus z squared. Okay. We'll suppress it, and we'll assign it to have the variable name triple integral, and we'll use, as we stated, integral 3. And we want to integrate the function g, and I didn't specify a region here, but we'll just use a rectangular one. And the x, y, and z, how about we just go 0 to 2 for each one. All right, and there's our triple integral. All right, all the things we calculated there. All right, and that is it for today.